Yeah, should be up, right?
Oh, great. I was hoping somebody would talk about this.
Okay, so for my project, I've decided to do sort of a deep dive into automatic differentiation, which is how most modern machine learning, software ecosystems handle gradients. Uh, yeah, in the spirit of, machine learning, I've decided to choose like a pun for my title. Because I've noticed that most machine learning papers nowadays, they're just coming up with new and creative puns for titles. So just getting in the spirit. Okay, so let's dive into it. And first up, yeah, what's a gradient? I think all of us are pretty familiar with what a gradient is. It's pretty simply speaking, it's a rate of change of function at any particular point. And we've traditionally thought of them as slopes, but if you start looking at it in a higher dimension, then I think the figure on the right sort of explains it. It's like like a vector that's coming out at a certain point. That is what you think of as that'll be like the geometric interpretation of gradient. And that's pretty basic, so I'm just gonna speed right past it. And yeah, the need for gradient is why do we need gradients? So the first use case of gradients would be in something like a sensitivity analysis, where you want to understand like how the change in, let's say you change any particular input to your system, and then how does the output change. So that'll be like really interesting and something that we do quite often in many different fields. Like I just listed a few of them: engineering, finance, and so on. And an example here is from something from an aircraft design process where you sort of check the drag and lift and everything and see how it changes based on like the different configurations. And it's an example of some sensitivity analysis you do in engineering. So this is one use case, let's say, of gradients. And next will be optimization. And this is something we've been looking at like throughout our course in machine learning pretty much. Anytime we need to find some optimum where like gradients is gonna make they're gonna make our life a lot easier as opposed to doing something like an evolutionary algorithm. When you have gradient, you can sort of just go follow the direction of the gradient and find like the optimum point, right? So that's another use case. Another use case that I thought is pretty interesting is in Bayesian inference. The problem with Bayesian inference mostly that we know of is that the marginal likelihood integral, like this part right at the bottom, is evaluated. We need to solve this integral on the right hand side, and this integral is not always solvable analytically. So we come up with other methods to do the sampling, and one of the common methods is called like there's a family of methods called Markov chain Monte Carlo methods, and yeah, so the problem with these methods is that when you go to very high dimensional parameter spaces, then something simpler like a metropolis Hastings is very inefficient because of the course of dimensionality as we discussed. And one of the ways people have come up with to get over this is this new method called Hamiltonian Monte Carlo. So now we have this likelihood, and instead of just sampling randomly, they're using the information about the the curvature of likelihood and then trying to be more efficient in the sampling. This one I thought like a different sort, slightly different one, cool idea of using gradients. So this is another use case where you need gradients, and you can sort of see it in from this GIF too, right? Sampling is not random; it's kind of following the curvature of this likelihood. So this is where also where you need gradients. And how you can calculate gradients, I've decided to group them into four different methods. Like, this is not anything standard. It's just something like a very arbitrary that I came up with. So first manual differentiation is just you do the differentiation by hand, right? So like basic calculus classes, right? So but the problem again with doing your difference derivatives by hand is that not all functions can be differentiated by hand. They're not all analytically differentiable, right? And also, yeah, even if they are analytically differentiable, like it doesn't make sense to do all these different calculations just by hand. For example, like in neural
Have you
networks,
heard
right?
about
You uh-huh. Someone asked something? Okay.
No, sorry, something went off on my computer and I turned it off.
Sure, no problem. Yeah. Yeah, as I was talking, like even if you can calculate derivatives by hand, they're not always, practical. For example, even in neural networks, you could theoretically just do all the derivatives by hand and then feed like this big, massive expression to your, to your program. But again, it's not a very neat way of doing things. So next pretty popular one is called finite differences. So the idea is to calculate the gradient at any particular point, you just take like a small step size over here. So if you want to calculate the gradient at this point, then you would take the small step size to the right and then evaluate the function at this point and then just do, change in y over change in x and then get your gradient, right? So this is also a pretty popular one, and there are different ways you could do this finite differencing. You could go forward, you could go backward, or you could take the average of both forward and backward. So this is pretty popular in engineering, especially when you need numerical solutions of differential equations. And again, the drawbacks of finite differences is that you need to evaluate functions over and over again, right? So every single time you take a small step, then you need to evaluate the function. And if the function itself is too costly to evaluate, then it's going to take a lot of time. And the next major drawback is something called a step size dilemma. So ideally, you'd like to choose like a very small step size. So in this figure over here, the step size, if it is really small, then your gradients are going to be much more accurate, right? But again, if you go too small, then there could be some floating point cancellation errors. But again, if you go too large, you're going to get inaccurate gradients. So this is another error, and this can keep building up. Like if you have massive programs, then so finite differences also no good. And the next one is symbolic differentiation. So this is actually a pretty interesting idea. So here you would represent functions algebraically instead of just representing them as numbers, as floating points. You'd represent them as algebraic objects. So one small example I've given away is when you're telling your computer y equals x squared, then you're telling the computer that y is like an object, right? It's a variable, and the square thing is an operator, and so on. And yeah, for this, you'd give some sort of chain rule. You'd feed it like some chain rules of calculating gradients, and then could like keep doing it. Sort of like it's like doing band, but with the help of a computer, right? So this is one way of doing derivatives. But again, the problem with this is that there's something called an expression swell. So even if you start with something relatively simple, the problem is that whenever you have any sort of product between two things, then now it's gonna be like a sum of two different things, right? So it can grow pretty quickly and become like exponentially large. Like say just a derivative is gonna keep growing too large, and then that's gonna have like implications on memory. So it's also not a very neat way of doing things. And finally, the way that we've settled into doing derivatives for machine learning is something called automatic differentiation. And the idea behind AutoDiff is that like any computer program that you can think of can essentially be boiled down to just very simple algebraic operations, right? Just sum and multiplication at the end of the day, right? So even something like, let's say, a sine function, let's say, so our computer would do that is to, for example, let's say do the Taylor series, and the Taylor series again is like a plus and products, sum and products. So every computer program can be boiled down to this two operations. Like not every program, but like for most general cases, let's say they can be boiled down to plus and multiply. And again, we have chain rules for sum and products, so we can just keep doing chain rule, right? So the idea is that you just keep doing chain rule and then keep propagating the derivatives all the way from the input to the output, right? So that's the core idea behind automatic differentiation. And yeah, so one representation that we use is they sort of take your computer program and then represent them as a graph. And most computable by most functions, I mean any computable function can be written as a directed acyclic graph. So directed would be just that it flows from one direction to other, like so from the input to the output. So that would be the direction. And acyclic means that there are no loops, right? So if it's a function, then there's not going to be any looping back. So as an example, I decided to pick this simple function probably not the best choice of functions, but just something to get an idea of what it would look like, right? So yeah, so this is how you'd go about doing this. So there's at the nodes you have both uh, variables and also operators, and then the edges sort of mm, they represent like the flow of information almost, right? So the flow or the order of operations, yeah, and the relationships between these. So this is how you'd represent a computer program using a graph. And yeah, there are other ways to represent a computer program too. Another very popular one is something called a Wenger tape, where instead of using a graph, you just use like a series of like the same thing, but you translate them into like a list, a big list, but make sure that the order is correct, right? So you're doing essentially the same thing as here. So there are some ways you can represent your computer program. And yeah, one popular way of getting derivatives now from this graph is to use something called forward mode. So yeah, let's just use the previous example. So yeah, you can imagine like the intermediate variables, like I've given them some names like v0, v1, and so on. So what you would do is like in the first step, when you're calculating this function, first thing you would do is take x and then square it, right? And then at the same time, you also store the derivative. So the derivative of x squared would be something like a 2x, and then immediately you evaluate it and you store it. So at any particular operation, you're doing the forward pass, and then you're also calculating the derivative and storing it right away, right? So that is what you do in the first step, and then in the next step you move on to V2. And now here the really cool point about doing this is that when you now need to calculate the derivative of V2 with respect to the original variable V0, so you do chain rule, and then like V2 with respect to V1 you can calculate right away, right? So it's just sine, so that'd be something like a cos. And now this particular term over here, dv1 by dv0, is something we've already stored in the previous step, right? So now what this allows us is we can just forget everything about the first variable, right? So we no longer need to store the first variable, and we just keep moving along, keep chugging along. So the same thing for v3, and then the same thing from v4, and then like at every step you're forgetting previous more than one step. The nodes that are more than one step behind, you just keep forgetting them. You store the derivative as well as the values at the same time, right? That would be your forward mode automatic differentiation. And the next way of doing this is something called reverse mode automatic differentiation. So here the idea is that um, you first do your forward pass, so you calculate all the values. So you calculate v0, v1, like let's say x is equals to something like it's a 2, then you just store all the values. So you store the value of x squared, you store the value of sine of x squared, and so on and so forth until like right at the end. So that in the forward pass, you only store just the values, just the intermediate variables, and now you can go backwards, like you're doing the same thing but now you're going backwards, right? So what you do now is, so the first step is pretty elementary. So if you look at v2, then we can now ask what's the derivative of this final term with respect to this particular term right now. And for now this is pretty easy to evaluate because v4 thing is essentially v2 plus v3, right? So now this derivative over here would evaluate to 1 right now. But if you imagine that instead of this being just v2, it's something like a v2 squared, then over here we'd have something like a 2v2, right? And now we need the value of v2 that we had uh, stored in our forward pass, right? So that is what you do. It's the same thing, but kind of backwards. And if you move along, like once you have the derivatives from v2 and v3, now you can go to v1, do some chain rule, and then you just keep doing this and until like at the final step you get dv4 by dv0, right? That is the reverse mode automatic differentiation. It's the same thing, but you're just going backwards. Now it might look like they're both the same things. Why am I spending so much time, trying to explain forward mode and reverse mode? They're just chain rule at the end of the day, but there's a pretty big difference when it comes to, especially when it comes to neural networks. And I'm gonna get into it. So that's a bit more mathematical. So let me see how much time I have. Okay. So you can, the thing that I represented earlier in a graph, now you can sort of imagine in an arbitrary sense that any function, you can imagine them as like a chain of elementary functions, right? Function compositions, especially, right? So I've taken an example of what you would do in a neural network, right? So in a neural network, what you would have is a scalar valued loss function. and you take a parameter, like many multiple parameters. In case of neural networks, that would be like millions and trillions. And then from that, you would just get one value of loss, right? Just a scalar value, right? From a vector to a scalar. And you can imagine that in that process, along that graph, there's like many different operations going on, elementary operation going on, and for each elementary operation, you have your rule, right? You have a derivative rule. So, and now what you can do is we have this neat rule for chain rules for function compositions, and we can use this similar rule for this thing over here when you're calculating loss. And if you look at what you'll end up getting is an expression something like this, where you've just simplified this gradient all the way to this products of this individual gradients, right? So this is just chain rule. Um, but the point now is that so then when you need to evaluate this product, there are two ways of doing this product, right? You could multiply it from the forward, so you could sort of group them like this and do this multiplication first and then move on all the way to the right, and that would be reverse mode. But if you instead you decided to group from the right hand side and then go backwards, that would be forward mode. So this is kind of confusing because I'm saying backwards, but you have to understand that the first operation that you're doing is D1, right? So if you look at this thing over here, so so the very first operation that you're doing is G1, right? So in fact, going in this direction is actually going forward. So this can be a bit confusing. So I thought I'd clear that up. So so when you start doing your product from the right hand side, that would be forward mode. And if you do it from the left hand side, that would be reverse mode. Essentially the same as earlier. Um, and now the question is, should you multiply it in the forward mode or should you multiply it in the reverse mode, right? And for this particular example of neural networks, what happens is that because we have a scalar valued loss function, so this first term over here looks something like this. So this is like a row vector, and then every other term in this big chain rule thing are just matrices, right? And now if you just look at this matrices, this chain of matrices, you can see that multiplying from this side over here makes a lot more sense because you're reducing the number of operations, right? You're just doing row operations first and you're reducing the size of the matrix all the way to the end. But if you do forward mode from the end, then you just keep getting matrices all the way and it'll take a lot more operations, a lot more addition and multiplication operations. So this leads to like the major reason why we do reverse mode in neural networks is that we have this massive number of inputs. So the output dimensions is way less than input dimensions. So this is applicable for neural networks, right? And that is why we do reverse mode automatic differentiation in neural networks. And this reverse mode AD is also called, but it's very similar to backpropagation, right? Backpropagation you can think of essentially as this reverse mode automatic differentiation. And again, like this all sounds very wonderful, but again, the problem with reverse mode is that you need to keep storing the intermediate variables. So you need some memory for it. And at the end of the day, there is no ideal solution, right? So there's no pre-lunch, so to speak. So that's just a bit of deep dive into automatic differentiation. And I think that's all I have for my project. I decided to do sort of a deep dive into theoretical concepts behind AutoDiff. And the applications would be like, how would you apply AutoDiff in ideology? So there are many software frameworks that have already been built and that are pre-built with AutoDiff. So some pretty popular ones are PyTorch and TensorFlow. And there's one called Jax that is sort of gaining ground. And Julia is also doing some good work. So there's many different software ecosystems that are already come pre-built with this AutoDiff capabilities, right? So now what we can do is when we're trying to do our physics and neural network integration, we can write our own functions. And essentially the AutoDiff will handle everything inside and they can calculate all the gradients and we can now do back propagation and train everything all at once end to end, right? So what we were seeing in some of our papers is that one of the papers used a surrogate. I think the Transformers paper, they used a surrogate to sort of integrate physics and machine learning, right? And because they didn't have like a really neat way of integrating both of them, they decided to essentially turn their physical models back into a neural networks and then just do everything in their preferred software interface, right? For now, we can just write anything. We can just write equations and then return back the derivatives, and we can do training, right? This is a pretty big application and a pretty big area of research right now in hydrology. It's called hybrid modeling. And it's also where I'm doing my research. And if anyone wants to talk more about this, I'm always up for it. So yeah. So finally, the limitations again, gradients are not a panacea. So there are many problems with gradients. Again, it comes back all the way to no free lunch. So there, if there are local minima, saddle points, then gradients can cause some problems. Again, there are known problems with vanishing and exploding gradients. And again, if there are loss function itself, like for example, a binary loss function like a 0 or 1 is again non-differentiable, right? So if you have non-smooth functions like this, then again, gradients are not going to work. And again, memory, as I talked about earlier, and yeah, if the gradient surface is non-smooth and there are many peaks, some high frequency components, then again, it can take some time to converge to hopefully like global optimum, right? So, yep, these are some references. If anyone wants to dive deeper into this, I'll send out the slides later. And yeah, thanks for your attention.
Thanks, Naveen. That was very useful. I have a question, but let me see if somebody from the audience, the group, has a question first. So as I mentioned and Naveen referred to in class, I didn't actually talk about the training method and how you do backpropagation and so on. So this helps a lot with understanding that. My question, Naveen, is so it appears to me that the methodology, which the software environment that actually does this, then already needs to have a library of derivatives, symbolic derivative for typical elementary functions that are typically used, correct?
Yes, yes. So yeah, they have their whole library. Yeah, they have their whole list of things. Yeah.
So if it has to know that the derivative of sine is cosine and so on and so forth, right?
Yeah. There are, I think, some more like some people are trying to build some elegant solutions to this. Like as I said, you can go all the way down to the Taylor series and start building derivatives back up, right?
Yeah.
There's some attempts of doing this, but as far as I know, in something popular like a PyTorch, for example, they just have their symbolic derivatives. It's preloaded.
The reason I'm asking this question, Manuel, if I seem to remember when I was visiting you and Eduardo a couple of years back, uh, Julia or some other approach uses something based on complex numbers to do that, where you don't have to actually provide beforehand the actual symbolic derivative. Is that correct, or am I misinterpreting?
No, I think the dual numbers are also applied here, but it's you're
Number
not
approach,
giving
yes.
you're not giving the symbolic derivative, but you're calculating it using the dual numbers.
Okay. So I don't know if you've heard of that approach, Nabeen. It's called a dual
Yeah,
number
it's called
approach.
Dual numbers,
yeah,
yeah.
dual numbers is sort of like a data structure almost, like so you
Mhm.
as I was
Yeah.
saying earlier in forward mode at least. Let me pull this up real quick. Let me go fast. Ah, yeah, so at any point you need both this and these two values, right? So you store them in the same number, we call it dual numbers, and then yeah, some cool connections with Taylor series expansions and stuff. But, yeah, that's I think mostly done in forward mode. I think could be
Okay.
done.
Yeah, but that's something I wasn't aware of before. But it makes sense. You have to store a dictionary uh, of basic alphabet of functions that you're going to use. And if you're using rectified linear units everywhere, it's very straightforward, right? Because the derivative is one, basically. Um, but if you're using more complicated activation functions, then you need to know what those derivatives are. That's cool. I didn't completely understand that before. Okay. Very nice. Thank you. Any other questions, thoughts?
Just maybe a comment that when I learned this, I think I started to see everything as just do automatic differentiation for everything, just any kind of problem. But as Naveen said, it's not a panacea, so it has its limitations. So it's a very nice approach. It's not the only approach.
Sure. But it is an important part of the whole machine learning explosion,
Yep.
which has made possible a lot of the things we're seeing today. Yeah. All right. Very cool. Thank you, Nabeen. So